Yeah, so I'm going to pick off basically where a few people have left off before. Immanuel Doc talked about Fermi-Hubbard systems, so I'm going to talk about those. And I'm also going to talk about photorons and how that relates to Fermi-Hubbard systems. So in the lecture tomorrow, I'll also get to things like machine learning. So that's a little bit more advanced, but we'll also apply it to these strongly correlated systems like Fermi-Hubbard model. Okay, so to start with, these are the people who are involved in the sort of work I will present. And on the theory side, that's Eugene and Annabelle. And then what you're going to see really resulted from many collaborations with experiments, mostly Immanuel Doc and Marcus Renner's group, and the senior people Daniel Guy and Christian Grusdt. Okay, and so now to get started, this is the overview of my lecture. Today I'm going to talk about boson photorons. Richard Schmidt already told you about these Fermi photorons, and here basically we're just going to look at impurities interacting with the surrounding Barton bosons. And I'll just give you a brief idea of how we can solve these problems. And then I'll apply these boson photon problems to look at this 1D Fermi-Hubbard model in a little bit more detail. And so the idea is, we have seen that in this lecture, for example, that these charges in the 1D Fermi-Hubbard chain, they sort of move around. And there was this argument that if you create a single hole in this chain, it should break up and form a spinon and a holon. And then the question is this holon totally free or will it interact with some surrounding? And the idea is actually it will interact with the surrounding. And that's what I'm going to talk about. I'll show you how you can, in principle, calculate what these interactions are. And then, of course, the idea is in the next lecture to contrast this to 2D, where these interactions are very strong, which changes the picture, and I'll tell you how. Okay, and so please interrupt me at any time to ask questions. I think it's clear, but it's important. Okay, so let's start with some motivation. Okay, so this is really supposed to entertain you a little bit and also make you think a little bit out of the box. So, first of all, this is where ultra-cold atoms stand today and trying to do quantum simulations. So, we came from quantum optics, and in quantum optics, the idea was to control individual atoms and photons at a very precise level. And Immanuel has shown in his last lectures that this is something they have absolutely achieved. In fact, to such a degree that now they can go and you put these individual atoms together to see interesting quantum many-body physics. Okay? So this is our starting point. The question is now, what do we do with these quantum many-body systems? Of course, we want to look at them, but we have to, we want to learn something about them. The question is how should we do this, and what types of measurements should we do to that? And so the motivation for me, one of the motivations is to look at the story how quarks were discovered. Okay, so let's just go through it and see how this relates to these strongly correlated systems. So of course you know the story, right? That at some point people look closer and closer at what the nuclei consist of, and then Gellman and Zweig proposed that that there are quarks that basically make up these objects. And so actually the story how this came about is quite interesting. So it started with measurements that physicists did in the 1960s, and they basically found out that okay, so these nucleons have a finite size, right? It's pretty small, but okay. At the time, actually, the great majority considered these particles to be soft objects with only a diffuse internal structure. Okay, and so and this is of course kind of reminiscent of also what happened when people first discovered atoms, right? The atoms were thought of as the most elementary particles, but then they found, oh, there's actually some structure, and here they found that there's a finite radius, and they thought of something like this Blum-Body model, right? And if you actually contrast this to strongly correlated materials, you will realize, actually, in high-temperature superconductors, the holes in these superconductors are actually also considered as soft objects by most people, okay? So maybe to just put this into context, right? So high-TC superconductors, they start out from something that we call, that's a Mott insulator. So you basically start with in 2D, right, with an antiferromagnetic pattern, something like this, right? And you get superconductivity by doping the system, right? So doping means basically number of holes, okay? So you basically have a few sites unoccupied in this antiferromagnet, and if you do this, that's where here you get the superconducting dope. Okay, so this is temperature, this is doping, and so you start from this antiferromagnet here with 0 volts, and then around 15 or so percent, 10%, you get this high temperature superconductivity. And so from just looking at this, it's obvious, it's important to understand what holes are. And indeed, it's not really known what they are. Many people think they're soft objects. And now, of course, with quarks, the story goes as this. Gell-Mann and Zweig, invented these. They basically found some group theory structure. I don't want to go into details. And in fact, the entire community was so critical that even Gell-Mann wrote that the idea is that these quarks had fractional charges, and that was something very shocking to the community at the time. And Gell-Mann, even though he invented these guys, he said search for quarks of charge, fractional. The highest energy accelerators would help to reassure us of the non-existence of real quarks, right? So, even though he invented them, he sort of thought they don't really exist. And then they did the measurements at MIT and SLAC collaboration. This is some cross-section. The key point is you see many counts at some high energies, okay? And this is, of course, totally reminiscent of these experiments that Rutherford did, and he discovered the story, right, that the nucleus is actually a solid object, and in pretty much the same way, the quarks are then established as the constituents of the nucleus, okay? And so, this is really the point here, that in order to find the quarks, one had to go to very high energies. So these scattering experiments push to high and high energies, meaning you basically look at the systems on very short time scales. And so I want to point this out because it also, if we want to think about the condensed matter context, this is a different regime than what condensed matter theory usually looks at, right? So Thierry was also talking about the low energy effective field theories. That's very important, but there's in some sense there's a little more to the physics because we can also look at very short times and very high energies, and the goal is to sort of repeat what they did with the quarks. Okay, so. Maybe, so you can finish, what I'm going to do in the lecture is basically tell you that the hope is to use these new experiments and basically find effective constituents, much like quarks. And of course, spinons and chargons that have been introduced by Thierry are exactly the analogs of quarks. So now the idea is to, we want to understand quantitatively what the properties of these guys are, how we have to detect them, and so on. And of course, this becomes particularly interesting in the future. Okay, and so maybe one comment where these experiments stand, right? So I do this plot. So here you have the temporal resolution of your measurements, basically how long it takes to to actually do the measurement, how long you probe the system. And then this axis I have the spatial resolution. And let's say the most important probes in condensed matter so far to probe high-density superconductors, they live on this side. So you typically probe in the frequency domain. So you measure for a while, and then you get frequency resolution. And you can do STM experiments where you have single-site resolution. You can also do things like ARGUS or RIX spectroscopy, where you have resolution of momentum space. So you basically need to measure over longer distances. And this is all probing basically this low-energy regime. And these monogas microscopes, in some sense, they sit down here in this corner. Because what they can do is they take instantaneous snapshots, so the time of the measurement is very small, and you really measure in time and space. So these are much more natural measurements in this system. But of course, we need a different interpretation. Now, one thing I should point out, and so Eugene reminded me about this when I showed this slide, is that of course solid-state experiments they have also powers to go to high energies. So in that sense, they can also go towards this side. But one thing that's really also unique, and that should also be taken in consideration, is that if you take a solid and you go to high and high energies, you have to worry more and more about phonons and things that basically go beyond the nice microscopic models that you know. And I think this is really a key advantage in these quantum glass microscopes, that we know our models and we can probe them at very high energies or very short times without having to worry about the extra degrees of freedom, like phonons that we may think are not so important for the physics we're after, but they can be. Okay, so yeah, let's pick off here and get into some more details. And so now, I'm going to continue on this board. Wow. So what's the best place to put it so everyone can see? Is this okay? Yeah. Cool, okay, so now I want to start talking about boson So the idea is, what this means is you have an impurity and you have some bath, right? And the idea is that the bath is described by some bosonic degrees of freedom. And that means the Hamiltonian you have for these bosopolarons is going to look something like this. You have a p squared over 2m. So m is the mass of these impurities. And then you have the free part for the bath. Okay, so omega k is going to be the dispersion relation of the, let's call them phonons, right? But they don't really have to be phonons. But we just call these collective excitations phonons. They're just some free bosonic excitations. And of course, Richard has told you about it. And then in principle you can have, of course what you need to make this interesting is interaction terms, right? And I'm already going to assume a particular form for the interactions, namely something like this. E to the ikx, and then we have ak plus a minus k times k. So this is one example of a bosopolar problem. Turns out it's a very well-known one. It's called a Fröhlich one, and that's basically at the core of conventional BCS superconductivity. So these interactions in BCS theory basically mediate the interactions between the electrons that would correspond to these impurities. Good. So far nothing much happened, right? And I will show you an example later what these VKs and omega Ks would be and what these phonons could be. One case you can keep in mind is for instance, this bath could be a Bose-Einstein condensate, and this could be an actual impurity atom going around. And later I'm going to discuss in more detail the case when the impurity is actually a hole and the surrounding excitations will be some spin excitations. Okay, so we're going to get to that too. But first I want to show you a little bit how to solve this model. Okay? So one thing of course you should remember is, right, we have operators x and p, they don't commute, and we have these a's. Okay? And they're coupled. So a priori this is not an easy problem, but it turns out to solve this you can use unitary transformations. So a little bit like Eugene was telling us about in the case of the Kondo problem. But here we use another one which is called the Lido-Pines transformation. Okay? So what we're going to do is we will transform the Hamiltonian by applying some unitary group. And we're going to define it in the following way. As e to the minus I x dot sum over k ak dagger ak. Okay. Does anyone have an idea what this could do, this operator? Or what it corresponds to? So one thing you note is sum of the k. So here we basically sum up the momentum of all the phonons. Okay. So this is our total momentum operator, p total of the bath. Okay. And x of course is the position of the impurity. And if you look at this, okay, so from the point of view of the impurity, p total is like a C number, right? Because x and p total commute. And that's just because impurity and these phonons are different objects, so they have to commute. Okay? So think of this as a C number for now, right? So in fact, there should be a head, here. It's an operator, but if you think about the impurity, you can forget about it. And of course, if you have an operator e to the I x dot p, what does it do? Almost, right? It's if x is the operator, it means it gives a momentum kick to the impurity, right? But you're also right that if we now turn around and we ask if we're the phonons, e to the I momentum times some, and now from the phonons this looks like a C number, then it's a translation, right? So in fact what we're going to do is we're going to translate all the phonons by an amount given by the position of the impurity. So imagine the impurity is somewhere, and now wherever it is, you take the phonons and you shift them by an amount given by the impurity position. What this means is if you have the minus sign here correct, I also always forget, but you figure out the right one. What you do is actually you shift the phonons into a new frame, which is co-moving with the impurity. So in the new frame, the impurity is always going to be at the origin, and it's going to be fixed. Okay. And okay, so the hope is that if we apply this, this should help, right? Okay, so now we're going to, let's call it LLP. What we're going to do is apply it to the Hamiltonian, and okay, that's the new Hamiltonian, right? It's called H theta. And we have to ask how it looks like. Well, now we have to, see how the unitary acts on these different terms. So one thing we know is if we have the momentum operator, we already figured out, right, that from the perspective of the impurity, this is a momentum shift, right? So that means the impurity momentum operator should be shifted by some amount. And the amount is exactly this P total, right? So it should be, we should get P minus P total for these phonons squared divided by 2, right? Because we shifted the momentum of the impurity. Okay, that's cool. Then how about the next term, the free phonon frequency? So we know we figured out before P total is like a translation, right? Now that means if I have something that's translation invariant, nothing's going to happen, right? Is this term translation invariant? Yes, it should be, right? Because it's just a free phonon dispersion. So that means this term doesn't change. That's nice. Okay. Cool. Now what about this term? Okay, here one has to be a little more careful. Turns out AK creates a phonon, and here we have a number operator, so they shouldn't commute. But it's easy to figure out, what happens. And I mean, it's a little exercise you can do. You can do it later, but I'll tell you the result. You will get an e to the minus ikx shift here from this guy. And this term, of course, only has x, the impurity operator x. And here also only x appears. So obviously these two commute, right? So this piece commutes. Here we get e to the minus ikx, which actually means we basically cancel exactly this term, right?
X also is okay in
The x? Yeah. Oh no, x is a different a than b. So okay, so I think what you're thinking about is you're saying, oh, if I add x and p, I can also go to a new harmonic oscillator a and a dagger, right? But these a's are completely different a's than all these a k's. Yeah. Good, right. Well, right. Okay. Cool. So then, let me write these. Okay. So then we eliminated this term. Okay, and then we have vk. Okay, and now of course, if you look at this, you will probably be happy because you can see that x no longer appears, right? And of course, the mathematical way to formulate this is that the new Hamiltonian H tilde actually commutes with P, where P is the impurity momentum, right? Okay, this is great, right? Because it means we found a conserved quantity in this Hamiltonian, which is the total P, right? And from now on, we can treat it as the C number. That's cool. Okay. Okay, now we have to solve the remaining problem. And of course, having eliminated this guy comes with a price. And the price is that, so, if you look at this term here, that looks nice, right? We only have quadratic terms and linear terms. And, such types of Hamiltonians can easily be solved by coherent states. And, I'll sketch that in a minute. But here, if you remember, this P total was this guy here, right? And this P total is quadratic in the a's, but, we square the whole thing. So in fact, we get a P total squared here, which is quartic in the a's. And that means our model is, no longer quadratic, and we can solve it exactly. Okay. But now, of course, the idea is to make some approximations, and the approximation is motivated by looking at the m equals infinity. Okay. So in the m equals infinity limit, of course, this first term just drops, and we can, as I said before, right, we can exactly solve this problem. And in fact, because we like unitary transformations, let's also formulate this again in terms of unitary transformations. So maybe you remember, right, from your textbook stuff that coherent states solve these quadratic Hamiltonians. So let's write down a coherent state. and we can write it as U alpha acting on the vacuum, where U alpha is some unitary operator, which is something like this. Okay. So that if you want to know the actual plus or minus signs, they will appear in the epsilon state. They might be wrong here. Okay. So that means we found a new unitary operator, this one, which is a very promising one to use, right? Now, what we're going to do is we're going to define h tilde tilde in this at m equals infinity, and define it as u alpha. They got alpha, let's say in alpha case, right? So these alpha cases are just C numbers. I didn't say yet what they are. We take the h tilde for the infinite mass, u alpha, and we take the thing. And well, the important thing is that if you remember what these coherent state shift operators do, what they do is actually you get u alpha acting on ak dagger alpha gives ak I think plus alpha k. Okay. So these coherent shift operators, what they do is they actually shift the a operators to a plus some c number. And now, of course, what you can see is that we have linear terms here. We shift them, so if we get plus some c numbers, we just get a c number, that's fine. But if we have a quadratic term and we shift each of them, we get some cross terms, right? Which means we actually generate new linear terms in the a's, right? And then the rule of the game is simply determine your alpha case in such a way that the linear terms cancel. Okay? And it's an easy enough calculation. And I'll go through it in detail. But what you get in the end is that the result is, of course, the quadratic part remains unchanged, right? And then you will eliminate the guys, so you get something like this. And your alpha case that you have to choose is minus. It depends somehow on this VK scattering amplitude and on frequencies. Okay. Good. So let me turn. Can I just turn this around like this? So now, of course, we went back to this m equals infinity case, and then you could say, why did we do all this hassle with the little Planck's transformation? It's a bit useful. That's true. But now, of course, we will consider finite terms, right? And while we cannot solve the problem exactly, we can still try to do something approximate. And that's what we're going to do. So what we're going to do is the following. Take the h tilde from this little pints at some finite mass, and we're going to apply this u alpha as we did before. And then I'm just going to project everything on the vacuum. And the idea is to say this here, u alpha on 0, we consider as a variational wave function. Okay. Which means that this thing that I'm constructing here is the variation energy. We also call it field energy. It depends on all these alphas, right? And so this is some classical, function. It's just a function of some c number of variables alpha k. And now what we're going to do is we're going to minimize this guy. And the way to do that is we just calculate this variation delta E naught delta alpha k for all these alpha k's. And say it's 0, so that's the saddle point condition. And, okay, again, I'm not going through the details. It's actually not a difficult calculation at all. I just want to give you an idea how to solve this, and what you're going to find is actually the V case, the optimal mean field ones, will look like this. So it looks almost the same as before. We have a scattering amplitude divided by some frequency. And this frequency turns out is given by omega k plus k squared over 2m. And then minus k dot m, k dot m, p minus pv field. And pv And so remember, this was this impurity momentum that was conserved in the Liouville frame. And we at this point we treat it as a C number, right? Because I told you before that this little Pine Hamiltonian commutes with P, so we can consider it as a C number. And so what you find, of course, is we start with alpha K mean field, we get some expression, and in the expression itself, alpha K mean field shows up, right? That means you actually, that's typically for mean field theories, you have a self-consistency equation, you have to solve it, and then you have it. And of course, in practice, you would do this with a computer, and it's easy enough to implement, and you get the results, right? I'm jumping over these different steps, but I just want to give you an idea how, show you that this is actually not so hard, right? These are things you can easily do if you want. You mean in the different mass case? Yeah. The intuition, the mathematical structure tells you that it's going.
So the masses are equal, that means.
Yeah, the mass is the mass of the impurity, right? I mean, our motivation to use these coherent states as a variational state for finite mass, of course, is because we know it works at infinite mass, and so, we basically think it's a good starting point, and then we proceed. And, we looked at this in great detail. It turns out it's indeed a very good variational wave function. But that's often the case, right? It's often hard to tell why exactly is it a great wave function, right? So this limit, of course, we have good reasoning, but then.
I have a question for the infinite mass case.
Yep.
They determined the alpha such that they cancel the interaction term. And what happened then? Was that an exact height state then, or?
Yes, in the infinite mass case, yes.
Oh, okay. And then you say, okay, for the finite, it's probably approximately, and you do variation, and you get something similar.
Yeah, we know it's approximate because it's the classes of models that are diagonalized by computer states exactly the quadratic. And you have one. Yeah. Right, and so now, when you go through all these details, one of the things that sort of fall off, which is nice, is you can, for instance, fairly easily do a perturbation theory now in decay, right? So if you assume your interactions are small, you can basically do perturbation and decay, and then you can calculate a bunch of things, right? And one of the things that's most interesting is you calculate the energy as a function of the total, so this mean field energy is a function of your total momentum. And what you're going to find is some E0 mean field at p equal to 0. So this is actually fairly easy to get because you have some spherical symmetry, and the self-consistency equation is easy. And then you get terms which are like p squared over 2m star for some numbers m star, and so on, right? So I did an expansion in p, basically, Taylor expansion. And you can get this coefficient m also, m star, and for instance, if you do perturbation theory, you'll find m star inverse is going to be m inverse minus, and then some integral, right? So don't worry about writing this. This is just an example, right? So. Okay, so this is the expression you get for the effective mass. Okay, it's a perturbation in decay. One thing I want to draw your attention to is this minus sign. Okay, I'm plotting m star inverse, so the inverse renormalized mass of this guy, and we see, it's clear that we can understand it as the mass because we derived the dispersion relation of this tolerance. So first we have p squared over 2m, and now it's a different one. And what we care about, of course, is what's the sign, like, does the mass go up or down, right? And we look at the inverse, and there's a minus sign. That means, both go in different directions, which means m star is actually going to be bigger than m, okay? Cool. And this is actually expected, right? That's what Richard was also talking about. You have an impurity, it moves around, and it drags with it a cloud of phonons, and that, means that the mass of this object becomes heavier, and that means so this would be this E0 mean field, got the energy as well. And the fact that this parabola is below this one, that's the curvature is the m star coefficient. Any more questions so far? So maybe one thing I can say while I'm erasing the board is that I told you of course that if you have impurity atoms in the BC, they will be described by these types of models. And that's a very interesting topic, especially when the interactions between impurities and bosons become very strong. And there have been some very nice experiments, but one of the things that's actually outstanding in these experiments, at least beyond one dimension, is an actual measurement of these effective masses. And I would say that in that case there's actually even some controversy to some extent. If the effective mass is much heavier than the bare mass or not. So that's just to show you that there are very interesting, still open problems in this field that we are working with us. Okay, so now I want to give you an yes.
Just to follow up on the last thing. So in the Lilo-Klein spring,
yes,
the impurity state is actually still a momentum eigen state, but with a different dispersion in the Lilo-Klein spring.
So in this Lilo-Klein frame, yes, but of course, once if you do unitary transformation, you have to be very careful, and you have to be careful about how to interpret these conserved quantities in the lab frame. And it turns out if you do it, and that's not surprising, the original full model was translation invariant, so the full total momentum of the original model is conserved, and that's exactly what the conserved quantity is if you re-express it in that frame. But the actual impurity moment in the lab frame is fluctuating, right? Because it keeps scattering on frames. Yeah, good point. Okay. So now let's move to the 1D Fermi-Howard model. And of course, I don't, I'm in a luxury situation since we already heard Thierry's and Immanuel's lectures on this. So I think, do you want me to write the Hamiltonian again? Maybe it's useful, right? So the Hamiltonian is going to be minus t, and then we have sum over nearest neighbor sides, and then we have sum over the spin degrees of freedom, ci sigma dagger, c sigma, Hermitian conjugate. So this is the hopping term, and then of course we have the Hoppertine term, sum over all sides, and side j for the upspin times n of j dots. Okay. And in all that I'm going to talk about in the rest, I will be interested in u much bigger than t. So basically the strong coupling limit. And in that case, we also know that the system will be in a mod phase. I'm also going to assume that n up plus n down, this should be less or equal than the length of the sides. Okay, so that basically means I look at whole worlds. And Immanuel also, I think, briefly mentioned it, that if you do with doublons, you can actually, there's an exact symmetry of this model. If you replace all holes by doublons, you basically get the same physics. So this is sort of without loss of generality. I'll just always talk about holes, but I wouldn't have to know. That's the middle. Okay, and then in this regime, of course, the relevant eigenstates are the following three ones, right? And number one is a hole, the other one is spin up, and the third one is spin down. And basically, the large U forbids double occupancies. But of course, we also heard in Immanuel's lecture before that there's super exchange, right? So for the super exchange, these states are actually important to be allowed at the virtual level, right? So what happens is the atoms can virtually occupy these double occupied sites and then go back very fast. So this is basically you should think of these as the quantum numbers we use to label our states. So these are the good quantum numbers. And then as a result, we will get spin exchange between these guys, right? And of course, the way to formalize this is to write your spin operators. You define at each site, you define a spin operator as I, and you just define it as Ci alpha dagger, sigma alpha beta, Ci beta. Okay. So it's implied that I basically sum over the spins alpha and beta. And what's happening is, so Ci alpha and beta, those are the fermion operators. And sigma, that's a Pauli matrix. It's a vector because we have x, y, and z. And it's a matrix, so it has two indices, alpha and beta, and we sum over those, right? So this is how you define the spin operators. And then we also already heard that, of course, if you consider the mod insulating case at half filling, meaning no holes. So that's the sort of the starting point, the simplest case. your effective Hamiltonian is going to be J times sum over the ij Si dot Sj. So it's an anti-ferromagnetic Heisenberg. Okay. Is this clear until here? So this is really, that was captured by the last lectures. So this is the result of the outer moment. In a minute I'll introduce the whole. So one thing that I want to also show here is actually what happened. So Thierry, this last lecture showed that you can basically solve this model by the bosonization, right? And he presented some low energy quadratic Hamiltonian. And what this actually means is you can, a quadratic Hamiltonian you can usually express in these ladder operators, the bosons. And you can actually do that, and if you use this translation. And what you'll find is that you can write this at low energies as something like a ground state energy plus a sum over k's, and then you have some collective spin excitations. They have a dispersion relation v, that's the speed of the spins, or the speed of these collective excitations times the absolute value of the momentum. It's a one-D momentum, right? So no vectors. And then you have bosons aka aka. And these are just the quadratic modes of this quadratic Hamiltonian that here showed us. And in principle, there are these other terms which are irrelevant, and so at low energies we can write it like this. The reason I like this, of course, is because we want to draw analogies with these polarons, and this looks exactly like the term we had in the polaron Hamiltonian. Okay, it turns out if you use this beta ansatz that we've heard about, you can find exact expressions for this guy and for this guy, and you won't be surprised that these these collective excitations somehow given by the super exchange. And okay, the prefactor is pi over 2. So it's known. That's all we need to know. Okay, and now of course we want to dope the system. And the idea is to consider a single hole for now. And that means we can actually think of it as an impurity. Okay. And of course the idea would be that this impurity would somehow interact with these collective excitations and form some sort of polaron. And what we're going to be interested in is how much do these terms, these interactions with these collective excitations actually change the properties of this polaron. And there will be also some other things that will be a little bit special. So as a first step, let me introduce another effective model, right? So we are sort of used to this now, right? We start with Fermi-Hubbard, and then we sort of integrate all these double occupancies. At half filling, we get the Heisenberg. And, we want to do the same in the presence of doping. And if you do that, you basically get something people call a TJ model. It's a little bit more tricky than that, but I'll show you why. So the idea is, of course, if two sides are occupied next to each other, you still get the Heisenberg term, right? So the effective Hamiltonian you get, you basically expand in T over U, right? In orders of T over U. And the first term you get is the Heisenberg term, as before. And of course, also what you see if you look at this definition of the S operators, if there's no hole, this guy is, simply becomes 0. So this term itself will basically only affect sides that are anyways occupied with spins. Okay, and of course in addition, well then that's also obvious, right? If you have a hole and there's a tunneling term in the Fermi-Hubbard, the hole will start to move around, right? So there will definitely be some tunneling term, it should be minus tunneling, and clearly it's also something like ij, and then some tunneling, right? And so this term is actually ugly to write. Turns out we basically the best we can do at this point is to write it as before, as exactly the same tunneling term. Okay, so it looks like this. And now I'm asking you, is this correct like this? At low energies? Well, the thing is it's not, because of course we don't want to write this Hubbard Q term again. So what we have to do is we have to introduce a projector here. And this projector, what it does, it simply assures that we never generate any double occupancies, right? Because this term in principle has the power to do so, right? If you have two spins next to each other and we apply this guy, one possible outcome is that two of them are sitting on the same site. But if we first and behind project onto single occupied sites, so this projects on 0 or 1 occupancy on every site, then we're fine. Okay? So, you can imagine that this is something ugly, right? It's easy to formulate what it does, but it's very nasty to deal with because usually we like the C operators. And so we have to find a way around that. Okay, and then, so these two terms, at least for a single hole, that's what people call it the TJ model, okay? For more holes, there's an interaction between holes, but let's forget this for now, right? So this is basically the TJ model. Turns out there are also other correction terms. It's actually fairly easy to see, right? So if you look at this situation, imagine you have an up and down and a hole. Okay, let's draw the hole like this. And now you ask, is there any other process to order t squared over u, which is this lowest order, that is not included in here? So let me give you a hint. The first thing that's going to happen is that we tunnel from here to here. So that's order t, right? So this intermediate state actually also has an energy u, right? So in our perturbation theory, we expect three things, right? T squared over u, that's the j. So we have already used one t, we already get the u of the intermediate state. We have one more t left, right? So what can happen, right? One thing, of course, that can happen is that one of the spins basically hops back. That's exactly what gave rise to the spin exchange. But there's something else that can happen. Yeah?
It could hop into the hole.
Right, it hops into the hole, which actually means that this now spin, and the hole effectively moves here, right? So what you can see is that to this order, this actually looks like a two-side hopping term of the hole. And of course, it turns out you have a sort of freedom in which spin you use. So it will be some correlated term, which is something like the hole hops two sides, and at the same time there can be spin exchange interactions between these two spins. And that's something that's not included in TJ model, but it should be included if you work to this nice order, T over U, to the lowest order. The reason people don't include it is because the tunneling T of the holes on to nearest neighbors is of course much more relevant, right? Because T is much bigger than the J, right? So that's actually also a very important point. So in this limit, our T is much bigger than J, and of course this next nearest neighbor hopping term will be of order J, right? And so that's why it's often ignored, but it turns out, and that in some experiments in Munich, we also found that it's actually important if you look at the spins around the hole. Then these terms start to matter. Okay, but I just want to draw your attention to this fact. From now on, I'll ignore those terms again for simplicity. Okay. So how much time do we have left?
13 minutes.
Okay, perfect. Okay, so now we saw that these projectors are ugly and they make some trouble, so we want to find a way around that. And this is where the partners come into the game. And I think I'll start on the new side. Because it's very important. So maybe one thing I should say is that the formalism I want to present you now, the reason I like it is because there's a chance to take this formalism and carry it over to two dimensions. And of course, if you go to 2D, it's not exact anymore and so on, but that's the key motivation to introduce it here first in 1D. Of course, other methods are more precise in a way, and you'll see where the approximations come in. But this is a huge advantage, the fact that we can actually have a chance to go to 2D with it. And that's the thing to keep in mind also when we okay, so the idea is to basically introduce the analog objects to quarks in high energy physics. Okay? So it realizes our local basis states. Local meaning on every single site. We have three basis states. One is the hole. The hole. Then we have C at site J up dagger on the vacuum, and the other one is C on site J down dagger on the vacuum. Right? These are the three states that I allowed, and that's exactly the subspace that this P guy was projecting us to. Okay. Now the idea is the following. Let's write our fermions, C, J, sigma. Let's just do something a little bit crazy. So we write it like this. Okay. We write this fermion as a product of two operators, and this one we call it holon or charger. And this we call the spinon. Okay. And what we're going to do is, so that's something important to keep in mind. When we write down a new boson or fermion, what we always associate with it is a Hilbert space, right? In fact, so this guy is supposed to be a hardcore boson, let's say. And our spinon is going to be a fermion. Okay. So both of these come with two basis states. In total, 2 by 2 or 4 basis states. Okay. And what we're going to do is we're going to write this state as a state with one hole. So we're going to say these are the same states. This state here should be, a spin up. So we're going to write it as simply as F, J, up, dagger on 0. And this one is F, J, down, dagger on 0. And now you could say, well, we didn't gain much. But turns out, now let's ask again, what does this constraint mean, right? The constraint before meant there either 0 or 1 particle per second, and not 2. But now, the constraint becomes something nicer. Namely, we sum up both spins, calculate the number of spinons, and then we also sum number of these charges. And what will we get? Well, it's always 1, right? Because there's either a charge or a spinon. So our constraint now is inequality. Okay? And this is much nicer than our constraint before, which said that the occupation is less than 2, right? Now we say this constraint is exactly equal to 1. And this is actually similar if you go back to your math class. There you also learn that if you have optimization problems with some boundary conditions or some constraints, it's always nicer to have these constraints with equality signs than inequalities. And so this is okay. So now, one thing actually to keep in mind, that's very important. If I write this fermion as a product of this boson and this fermion, this is not true in general, right? You cannot just write it like this. But if you work in this reduced subspace where this constraint is fulfilled, then it's actually fine. Okay? So this is important to keep in mind, right? That we always have to keep this constraint in mind, only then we can work with these equalities. Okay, when we have this, we anyway want to work here. Now, what we're going to do is we're going to take the Hamiltonian again, right, let's say of this TJ model, right? And, okay, now you basically take your C's and you plug it into this Hamiltonian, and you write down what you get. And here's what you get. So, of course, when you have a C dagger C, you also get a whole hopping term, right? And let's say you go from side I to side J, the whole will hop. And then, of course, you will get some F terms. And they will look like this, right? And now something interesting happens already, right? The whole hops from I to J, but the spinon actually hops the other way around, right? So it hops from J to I. And that's because, one of them has a dagger, the whole has a dagger, the F does not. And so I actually changed the order here, right? So let's say I have C, C dagger, and then I should have H dagger H. Those are bosons, so I can change their order, but that actually means that the sign doesn't the sets change. And then we still have the sigmas, and we have to sum of the sigma. And we have the division point. Okay. Good. Okay, so the good news, of course, is we did get rid of the projector, right? Because, now we have these operators, but we always work in this constrained subspace, so this projection operator is gone, and that's great. And then, okay, you have this J thing, and so it turns out this is pretty ugly, right? So, of course, if you have S.S terms now, you basically get a bunch of terms that are order F to the 4, okay? And you will find them in my notes, and of course in textbooks you can find them, but I won't write them down. They're pretty ugly. Okay? But it turns out they're not so important for what we're going to do next, because we are sort of already. This is basically what's left over from this S dot S term. And we saw before already that we can express this in terms of these collective spin excitations. So we care more about this term. Okay. Now, of course, you would say, well, this is nice. We got rid of the projector, but now we actually have terms that are quartic in the operators. And this is very difficult, right? Usually we know how to solve quadratic Hamiltonians, but this is a very strong interacting one, so that's bad news. And now we want to play a nice trick. Right? So before I play the trick, let me ask you what you think one could do. Okay? What could you do to make progress on this? Well, one thing you can always do is you can do a mean field approximation, right? And it may be very bad, but you can do it. Turns out in this 1D case, qualitatively it's not so bad. And the mean field thing you can do is you can introduce expectation values like these. Okay. So the idea is to say that these f dagger f terms you replace by C numbers. And then, if you replace these by C numbers, you would actually get a quadratic Hamiltonian. And what it would describe is basically some charge up that's tunneling freely. And okay, because this is some number, our hopping would be renormalized, right? Now, of course, this sort of violates the constraint, right? Because the constraint is really nonlinear. It means a nonlinear connection between these f's and h. But then you could say, well, maybe it's fine if we just enforce the constraint on a mean field level. So we're not as strict. We just say this should be satisfied on average. And so it turns out this is not so bad, right? So you get sort of the right physics, right? You get charge-ons. They have a free dispersion, and this is basically one way of seeing already your first glimpse of spin charge separation. And you would also, in the same way, you can once you introduce these expectation values here and decouple everything. Turns out you also get some nearest neighbor hopping for these spinons. So you get basically a Fermi sea of these spinons. And it turns out if you look at the excitation spectrum and so on, this is actually a very good description of these spinons. Okay, so, but on the other hand, I should also warn you, right? If you do this and you're honest, right? You say you solve these expectation values self-consistently with this constraint, let's say on the mean field level, the actual numbers you get, they're horrible. They're pretty bad, right? So, you won't get quantitative results, but qualitatively it actually looks good. So this is the mean field ansatz. So the second thing you can do is you can play with geometry. And that's the trick I'm going to tell you next, which in this is actually nice to solve this problem. Okay, more questions? Okay, so this goes under the name squeeze space, and I'll show you why.
Question.
Yeah.
Unfortunately, it's about 8 bits erased, but that's fine. But in the TJ model, why do you still have an SI.SJ terms on sites, including where the hole might be?
Well, the idea is that this S itself is 0 if you apply it to an empty site, so it doesn't actually do anything.
Okay.
Yeah. Right. Otherwise, or you can say the spin is 0, so 0 does
Yeah.
Okay. So now, just to remind you, this is. I will discuss the same hole. The formalism I will present is easily extendable to more holes. It just gets more nasty to write things down, and you'll see why. Turns out, so what we're going to do is I'll introduce new F operators, and okay, they have an index J tilde and some spin. And what I'm going to do is I'll take the old F operators and I introduce a shift of the index by something that depends on the hole, okay? So this is pretty nasty. Okay, let me make sure I get all the signs right. So this is what we want. Okay, this looks nasty, right? Because you shift the index of these F operators by an amount which itself is an operator, okay? It's a fairly nasty construction. But it turns out it's not so hard to understand what's going on. And to see that, let me just draw some random spin configuration here with the holes here. Just any spin configuration. And so, before what we did is we labeled all the sites or the quantum states by what happened on the respective site, right? So we had J, and so this was that site 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what I did is actually now I say, oh, my new tilde operators are the odd operators at some J, which is shifted by something, and so this is the whole number, right? And I sum over all the the sites left of site J. And basically, so what I do is I ask, is there a hole left of me or no, right? If there's a hole left of me, I get shift. If no, I don't. Okay. And so what this means is I have new tilde variables, and I will basically do this. So now my J tilde here is 1, 2, 3, 4, 5, 6, 7, 8. So what you see, what happened is I just label the spins in the order they appear, and when there's a hole, I just say, this is the next spin coming behind that spin. So this spin, instead of being labeled by lattice site number 7, is now labeled by spin site number 6 in squeeze space, right? So the mapping goes like this, and you can see that there's sort of the shift here when we go across the hole. And it's called squeeze space, right? Because what happens is we basically we squeeze the spins together and remove the hole, right? And now the idea is that if I tell you the quantum state of all these F tildes, and I also tell you where the hole is, then you know what this state looks like, right? So if I give you this state, and in addition I tell you the hole is on site number 6, you can tell me, oh, that's actually this state, right? So we basically just did a relabeling of our states. Okay, and then it turns out, let's look at our Hamiltonian again, right? The Tj. Well, we get this hopping term minus t, and then we have sum over all nearest neighbor sites, ij. And we had what we had before is something like the I dagger hj, right? The tunneling of the charge on this whole lot. But now what you see is imagine this guy hops from here to here. What happens to the spins in squeeze space here? Well, nothing, right? Because if the hole goes from 6 to 7, this spin is still labeled by spin 6, and this spin is still labeled by spin number 7. And this actually means that we get a quadratic Hamiltonian, right? And this is really cool. Now we have something we can actually solve, right? Because it's quadratic. So we got rid of the F operators here. And so what this describes is basically a fractionized excitation, right? Because remember what we did is we took these electrons and wrote them as H dagger times F. So this is sort of like basically the charged part of the fermion, right? And it's basically freely tunneling. So this is really cool. Okay, and then in addition we have the J part. Now we have to be a little bit careful though, right? But it turns out it's also not very hard to see what happens. In fact, what happens is this. So of course we still get nearest neighbor interactions between these spins here, these J tildes. But we have to be a little bit careful, right? Because when there's a hole on this side, what happens is that the spin exchange interaction between these two spins, or these two spins, they're the same, is switched off, right? Because the spin exchange should actually only appear between spins that are next to each other. So I get spin exchange interactions everywhere for these so these are tildes, right? These are basically the new spin operators I defined from these F tildes, right? So my S tilde is defined as basically what we had before, except with the F's, right? With the F tilde. So J alpha sigma. Okay. And now you know there's what's nice is we could actually think of these terms, the last term here as two terms, right? This first, maybe taking this first term, that's our free collective or free spin excitations, right? And we know those are these K, V spin, K, AK, AK. And the second term corresponds to an interaction, right? But now it's a density, right? And density interactions are much nicer. And in fact, that's what we discussed at the beginning, right, with these polarites. It basically says if there's a hole inside J, there's some effect on the splits. Okay. And okay, so now I already did next first step is we basically replace this free spin part here by the free collective excitations. And then we should also think about these interactions more closely. And of course what we're going to do again is we rewrite the interactions. And the way we do it, we basically express these S.S terms here using Thierry's translation to bosonization. And then we also, introduce these A operators in these quadratic forms. Okay? And so, there are a bunch of terms, and I don't want to go through all the details. There's the references in your lecture notes if you care about all the terms. But I just give you a most important term for this discussion now. So, turns out you can write this as J as something like this. So there are a bunch of terms. There are some numbers here. This is a constant. It comes from beta ansatz. Constant we don't really care about. It's just a shift of image. Another constant. What I introduced here is M. M is the magnetization. So now, for simplicity, I assume that the system has some finite magnetization. And then we get terms here. They are also proportional to the magnetization in the system. Sum over all momenta. And then I get again a term which is linear in these collective modes AK. And then I will also get quadratic terms in the AKs. And actually, they are somehow the form AK, AK prime, and you can also get AK dagger terms. And you have to sum over Ks and K primes, right? So they're sort of a little bit ugly, but you can figure them out. Turns out these are there also when there's zero magnetization. And then you get uncapped terms, which is basically some cosines or something, right? So, you can deal with them. I don't want to go into details. The basic idea now is to say that what you see is actually what we get is exactly a Fröhlich polar model again, right? Because you have a free impurity, which is hopping on the lattice. And if you actually restrict yourself to small momenta, what you can also say is that it actually becomes something like a p squared over 2m term at lower momenta, right? Where m, the mass, is going to be 1 over 2t. Okay. And t is really this hopping. And then we get this usual Fröhlich term, and this would be your VK. with these numbers included, let's say. And then you can basically do the calculations that I showed you in the beginning, do coherent state calculation and calculate, for example, the mass enhancement of this guy. Okay. And okay, so this basically brings me to the end of the first lecture. Let's discuss now what we learned, right? So one thing I want to point out is the following. Maybe you can go back. So I showed you this perturbative expression for the effective mass of this polaron, right? And it was something like this. So you had 1 over the effective mass m star is going to be 1 over m minus something 1 over m squared, some numbers, and then an integral, and here you had something like a dk, I think squared, k4, dk, and here we had the omega k plus k squared over 2. Now what you can see is the following. Imagine your t is very much larger than j. Then the effective mass 1 over m is something like t, right? Which means 1 over m is actually large. Which means you divide by something which is large. Which means that this term is actually small. Okay? And the physics is simple, right? So the idea is you have this very light impurity, the hole, this charger, it's moving through the system, and then it scatters these collective spin excitations, and the energy goes like J, right? But then, if your mass is light, the recoil is huge, right? Or it has to be huge to scatter efficiently, which means it's very unlikely to happen. And that means that the effective mass enhancement is very small. Okay? So, this is a way of seeing that if I have these additional couplings to these collective spin excitations, the charge will actually be dressed with some spin excitations, but the dressing effect should actually be very small, right? And so this perturbative expansion that we did here is also, should be very accurate. And then, of course, there are these other terms that I showed you, but you can do the same reasoning, do the same perturbation theory in T over J, and show that the effective mass enhancement is actually tiny. Okay. So so what we learn is the following: we learn that we can write these fermions as these holons times the spinons. These holons, they move through these antiferromagnets, and they basically around the antiferromagnet, basically exactly around the hole there will be some small excitations of these of this spin environment, right? So indicating them by these little circles, right? So these spins will sort of adapt a little bit to the hole. So these holes are already fractionalized, right? But the fact that they're fractionalized does not mean that they don't interact with the collective spin excitations, right? They do, but we also saw that when T is much bigger than J, this dressing cloud is extremely small. So, there will be some mass renormalization, but it's extremely small. So that means it's essentially a free hole, and essentially the dispersion it will have is something like minus 2t cosine of k. Okay, and we have T star, but this T star is basically T. Okay? And then of course you can also continue asking, what are the spinons doing and so on. I don't want to discuss this now, but I want to, maybe close with one last remark, which is the following: these A's, these collective spin excitations that we had, those are not spinons, right? That's important to keep in mind. These are really some, in the end, they are basically related to pairs of spinons. So the idea is the hole moves and it can create pairs of spinon, anti-spinon excitations, and they, adjust to the hole. But that's important. So these are not spinons, right? The spinons have their own sort of life, and that's really the key of fractionalization, right? Fractionalization does not mean that these holons are not interacting with the surrounding spins. It only means that there is some excitation which has this fractional quantum number, the charge but no spin, and it doesn't mean they're totally free. And this is of course important if you go to 2 dimensions, because in 2 dimensions we saw that it's very natural in 2 dimensions already from theories, slide with the string, that they will interact. But the fact that they interact does not completely rule out the possibility of fractionalization or spin charge separation in 2D. Okay, so I hope that this gives you an idea of what the microscopic mechanisms are for the interaction between these guys and what's the way to describe them. And then next time we're going to continue with 2D. Thanks.
Any questions?
So on the other side of the board, I don't know if it's worth trying to diagram, but the final Hamiltonian before going to the low field, or the low energy field theory, these sums are on the real space IMJ, right?
Which ones? These ones?
Yeah.
Yes.
Those are not sums on ITAMP and or the reading index.
These are real. You
Yeah.
see there with the holes.
Yeah.
And yeah, so like here I always assume you have an infinite system, which is why, because these of course are newborns, right? And so then, if you have an infinite chain, you don't care about the edges. If you have edges, you have to be a little more careful. But I also use J because the holes here. But these S dot S, they live in this free space.
So those are okay.
And that's why you can see if you have more than one hole, the whole thing gets a little more nasty. But you can still do it.
Other questions? Could you walk us through when the hole moves to the right and leads to this quadratic part of the Hamiltonian?
Do the quadratic.
Yeah. And the Hamiltonian, you said the hole moves to the right, but somehow the spin doesn't reverse.
Yes. Well, right, so the idea is, we can do it, right? So if the hole goes from here to here, this one, these exchange, so this guy goes here, this guy goes here. So this guy, but you see it maps to the same one, and this still maps to the same one. So all that happens, the hole changes its place, but the spins don't react in any way.
Any more questions? If not, then thank you, Fabian.